So welcome back to another APAC seminar, everyone. So today we've got Alex Elzenaar from the Max Planck Institute in mathematics, and today he will be talking about what is a Kleinian group. Take it away, Alex.
Great. So I was asked to give a talk on an expository talk on some object or theory in mathematics. And so I'm not going to be talking about anything that's kind of research level. I'm going to start very basic and I'm going to get quite far. There's some stuff near the end that I've prepared on quaternion algebras and arithmetic groups. But depending on how everyone is going, I might go fast or I might go slow. It just depends on the kind of level of the audience. So I would appreciate it if I'm going too fast, if you could let me know in the chat at any point. So I want to start with some vague motivation, and the vague motivation is the idea that we can tile the plane with patterns. So these are some very old manuscripts. So the ones on the left are Byzantine and the ones on the right are Egyptian. And I just want to show that this idea that you can repeat a pattern and fill a space with it is something that did not arise when people started writing down groups in the 1800s. It was around a long time before that, and it's the fundamental thing which it's the thing which I want to view as the fundamental object in this field. The idea of this tiling of the plane. So there are two things that a tiling of the plane should have. First of all, your tiling should actually be a tiling of the plane. You should cover the whole plane. And second of all, your tiles shouldn't overlap. And in what I want to do today, I'm actually going to drop condition one a lot of the time. So my tiling is sometimes going to cover only a subset of the plane. I keep saying the plane. I actually want to work in more general spaces. So I've been a bit vague here and I've said geometric space. Really, it's going to be a Thurston geometry, but I don't want to define what a Thurston geometry is. It's basically a metric space that satisfies analogues of Euclid's classical 5 axioms. I've also said that the tiles are going to be polyhedra. This is also a lie. In general, my tiles are going to be open subsets, and they might be quite wild open subsets. We'll see some examples. But I don't want to get into technicalities about whether they have to have open interior or whether the boundary has to be linear. I really just want you to think of some subset which is being mapped around by a group so that it covers some subset of a geometric space in an isometric way. Just to show that this is a non-trivial thing to do, you may have heard that in R2, so the Euclidean plane, there are exactly 27 wallpaper groups, and these are the 27 possible tilings of the Euclidean plane via isometries, allowing rotations and reflections. More generally than the Euclidean plane, we can tile the hyperbolic plane. So this is a famous picture by Escher showing the disk model of the hyperbolic plane. So these lines here, these lines here are the geodesic lines in the hyperbolic plane. And this is a tiling by, so this is not a tiling in the sense that I want to consider it really, because there are two kinds of tiles. There are triangles and there are quadrilaterals, but nevertheless it's a tiling of the plane and it's got certain symmetries. And in fact, you can view, if you want to have the kind of tiling that I'm going to consider, you can view the fundamental tiling as being the union of one of these quadrilaterals with one of these triangles. And then this is mapped around by some group of isometries of the hyperbolic plane to fill the whole thing and give this tiling. Of course, here I'm ignoring this coloring. I only care about the shape. You could do the same thing in higher dimensions. So this is a tiling of hyperbolic 3 space. I forget exactly. I think this is a tiling by dodecahedrons. And this is actually giving a knot complement geometry. So this is not really a tiling of the, anyway, we'll get onto this. So we have a tiling of hyperbolic 3 space, again, by some group of isometries of hyperbolic 3 space. And here we have an actual polyhedron doing it. So we have a tile, and it gets mapped onto the whole space by some group. The picture looks like this. So this is the picture showing a square, and then maybe the group G is the group of translations. So I want to think of the plane as being the complex numbers. So that the translations might be Z goes to Z plus 1, and Z goes to Z plus I. So this is the group of translations that way and that way. And so one way of viewing this group action is that it takes the square and it gives you a bunch of copies which tile the plane. Another way of thinking about it is that it takes the square on its own, and it's mapped this edge to this edge, and it maps this edge to this edge. And if you just view the this action on the edges, then this group action is giving you the normal action which induces the torus as a quotient of the square. So here the two pairs of edges are mapped onto the standard homotopy basis for the torus. And it's a standard theorem in this kind of field that as long as your tilings are nice enough and your group is nice enough, then the action, so if this is all on X, the action of G on X, the whole space, induces the same quotient as the action of G on a single tile by edge pairings. So this is not T as a subset of X. This is T with the group action induced by these edge pairings. So just by looking at the action on a single tile, we can see what the group quotient is of the whole space. Going the other direction, we can take a surface, or just for the time being a surface, and we can cut it. So say we take the torus, we can draw a homotopy basis like this. We can cut open this holonomy basis, and we can unroll it and put it down on the plane to form a tiling. So this is what's called developing. And when you do this, you lift paths. So here's a path here with distinct endpoints. This lifts after you develop to this cover, which is so here's one individual copy of the surface after it's been unwrapped. So what we're doing is we're really just constructing the universal cover, but we're constructing the universal cover in such a way that we're preserving the intrinsic geometry of the surface. And when we keep track of the geometry of the covering map, which is going to be the fundamental group of the surface, isomorphic to the fundamental group of the surface. When we keep track of the embedding which this development process gives us in the group of isometries of the upper space, X, then this embedding gives us what's called the holonomy group of S. And the surface that we started with is isometric to the geometric space X, which we've developed onto. And this is given by the geometry intrinsic to the surface. By the uniformisation theorem, the surface has either spherical, hyperbolic, or Euclidean geometry. So there are three possible geometric covers: the sphere, hyperbolic two-space, or the normal Euclidean plane. So this is intrinsic. This geometry X is intrinsic to the surface, and then the holonomy group is giving you the information about how the geometry is sitting globally on the surface. So that's the theory in 2 dimensions. In 2 dimensions, we have three kinds of geometry, and we can produce this. We can write it. We can write every surface as the image of the quotient of some geometry under group action, and we can get that group action in a concrete way by doing this developing process, by cutting the surface open and unwrapping it. In 3 dimensions, it's a little bit more complicated. So this is now the geometrization theory of Thurston. So if we take a 3-manifold, then first of all, we have to cut it into pieces, possibly many pieces. And then once we've done that, each piece admits a similar kind of covering. There's a geometry X and a discrete subgroup of the isometry group of that geometry, such that the quotient of X by the group gives you that piece of the manifold back together with its geometry. And this group is the usual holonomy group of X, which you can define in terms of analytic continuation in the normal way that you learn in differential geometry. And of course, so when I write this theorem, this bit here is in some sense easy. So if you start with a manifold which you know is locally, well, basically you can classify all of the Thurston geometries and all of these manifolds as long as you assume that they can be written in this way. So if you start with geometric manifolds, then this bit here, the fact that they can be written as this quotient is basically easy. The hard part of this theorem is the fact that you can take an arbitrary 3-manifold and cut it into pieces. And this is the geometrization theorem, which was proved by Perelman via the study of Ricci flows in the early 2000s. For the sake of this talk, though, I'm only going to be talking about the situation of the second part. So we have a manifold which we know is locally geometric, and we know that there is a group G such that we can uniformize the manifold M via G. And in fact, we're going to restrict ourselves in a moment to just the hyperbolic case. But I want to actually show you what all the Thurston geometries look like, because there are only 8 of them, and normally you don't see this in undergraduate courses. So analogous to the surface case where there were 3 geometries: hyperbolic geometry, spherical geometry, and Euclidean geometry. In 3 space, there are 8 geometries. So there are the ones which you're familiar with up the top: hyperbolic, spherical, and Euclidean, but this time in 3 dimensions. And then there are some fibered ones. So you can take H2 and then so you take copies of the hyperbolic plane, but then your third axis is just normal non-curved lines. You can do the same thing, but with a sphere instead of instead of hyperbolic space. And then there are three weird geometries. So there's the universal cover of PSL2R, and this is the geometric type of the trefoil knot, for example. So this does actually arise in nature, even though it looks kind of weird and twisted. And then there's nil geometry and sol geometry. And it turns out, and you can justify this in various different ways, that most geometric three manifolds are hyperbolic, and the remainder are rare. So if you take a random three manifold, it's going to be hyperbolic. On the other hand, so these are abundant. On the other hand, these are also the hardest to classify. So in Thurston's book on the geometry and topology of three manifolds, all of these are completely classified. So you can write down all of the manifolds which have one of these geometries. There's a list of them that you can write down. For hyperbolic manifolds, this is not true. Or rather, by the geometrization theorem, you can start writing down a list, but the situation here is much more complicated. So that's the situation I want to restrict myself to.
Can I just ask a question, Alex?
Yeah.
With the theorem on the previous slide, so if you have a manifold and you cut it up into pieces, I assume that these corresponding Thurston geometries and groups are going to be different for each of the different pieces you've cut your manifold up into. Like, they're not necessarily going to be the same. Is that correct?
Yeah. So on the edge, on the bits where you cut, they'll have to match up, but otherwise they're different geometries.
Okay.
So the kinds of surfaces that you cut along are things like embedded terrae and things like that. I have no idea really what this looks like, though. I only ever really deal with ones where with manifolds where you have a global geometry, and that's in some sense the important case, because by this theorem you can reduce everything down to that case. So we know that if you start with a hyperbolic manifold, M, it's going to be the quotient of hyperbolic three space by some group, and that group lies in the isometry group. Everything is orientation preserving, even if I forget to mention it. So yeah, it's just a technicality, but some people, when they do this stuff, they don't preserve orientation in some places, but everything I write down is orientation preserving. So this group G, the Holonomy group, is going to be a subgroup of the isometry group with hyperbolic three space, and to get a manifold as the quotient, G necessarily has to be discrete. So what I mean by this is that G has a topology on it. It has the compact open topology as a space of functions, and in that topology it's discrete. I don't care about the details. We can be more concrete in an algebraic way about what discrete means in a bit. And then we call a group which looks like this a Kleinian group. So either it's the holonomy group of a hyperbolic three manifold, or equivalently a discrete subgroup of the isometry group of H2. And in a minute, I'm going to give a more concrete definition in terms of matrices. But before that, I want to give an example of some of the stuff. So here we have a construction due to Thurston of the knot complement of the figure 8 knot. So here we have the figure 8 knot. And this diagram is showing that if we take a tetrahedron, so really this is a tetrahedron in hyperbolic three space, and these edges are right out on the boundary. So these vertices are on the boundary. These vertices are infinitely far away from the rest of the tetrahedron. There is a way of gluing the edges of this tetrahedron together, just like we glued the edges of the square together earlier to get the torus, such that the resulting manifold is exactly a three ball with a copy of the figure 8 knot drilled out of the middle. So B3 minus the figure 8 knot is obtained by gluing the vertices of these tetrahedron, and hence the manifold, which is the complement of the figure 8 knot, is hyperbolic because it admits such a description. So I want to consider the group, the Kleinian group, which will give you this knot manifold as a quotient. And this was studied by Riley in the 1970s. And Riley wrote down a faithful discrete representation from the holonomy group of the manifold to PSL2C. So this is the group of 2x2 matrices of determinant 1 up to multiplication by up to sign. And this discrete faithful representation had this image. So it's a 2-generated group. And it's got this root of unity in there, but it's a fairly simple group. Oh, by the way, I'm going backwards historically. So historically, when these things were studied, people started with all of these matrices, and then in the 20th century, all of the theory of hyperbolic manifolds developed, and it was seen that this earlier theory agreed with this later theory. But so when I start talking about hyperbolic manifolds and then I use that to motivate this matrix theory, this is not at all how it happened geometrically. These matrices were studied by people like Poincaré, Klein, and Fricker and Fuchs. So these are much older, but for the purposes of exposition, I think hyperbolic manifolds are easier to motivate to start with. So we have a matrix representation, but we've completely lost any kind of intuition about what this is doing geometrically. So what are these matrices doing geometrically? And the point here is that these lie in PSL2C. So these are acting on the projective line over the complex numbers, or in other words, the sphere, because the projective line over the complex numbers is the complex line together with a point at infinity, which compactifies it. And if you take the complex plane and you compactify with a point at infinity, you get the Riemann sphere. So these matrices should be acting on the Riemann sphere. And indeed, this is what the action is. So they act as fractional linear transformations. If Z is, so this only defines it for Z and C, but if you take limits, you can define it for Z equals infinity as well. By elementary complex analysis, all of these linear transformations are products of reflections in circles. So when I say reflection in a circle, I take a circle, it has a center, and the reflection sends a point P to a point Q on this line, such that if R is the radius of the circle, the distance from the center to Q times the distance from the center to P is R squared. So it's a reflection in the circle. It maps the outside of the circle to the inside, and it swaps the center of the circle with infinity. All of these can be written as a product of an even number of reflections in circles. And these are called Mobius transformations. Reflections in circles are conformal. Hence, all of these maps are conformal. And by conformal, I mean the derivative, locally, these map preserve angles. In fact, every conformal map arises in this way, and so we have a natural isomorphism between PSL2C and the group of conformal maps on the Riemann sphere, and in fact, these are isomorphic as topological groups with the compact open topology. Again, I don't care what that topology is, but they're isomorphic as topological groups. And now to relate this with hyperbolic free space, we have the following picture. So I'll draw the picture in 2 dimensions. So here's H2. So I have an action on the interior, and I want to give you an action on the boundary. So the action on the interior will take a point P and move it to a point Q. If I take a point on the boundary, Z, then there's a unique geodesic through Z and P. If P gets mapped to Q by gamma, then the whole geodesic gets mapped by gamma to Q. So I get a geodesic over here. And in fact, if this geodesic is oriented, so I can distinguish these endpoints apart, then this image geodesic is also oriented. So I get some point W at the endpoint of this geodesic, at the positive end of this geodesic, and I define gamma of Z to be equal to W. So I've essentially taken a finite, so a isometry which acts on the space around you, and I've extended it to the points on the horizon just by looking along geodesics and seeing if I move the geodesic, where does the end look like it should go. So that's why this is called the visual boundary. And you can do this in the normal Euclidean plane. So if I take a point, I can define an action of, if I take the normal Euclidean plane and I compactify it to be the complex plane in exactly the same way that I've drawn here, except here this is the compactification of hyperbolic space. So here's the compactification of Euclidean space, P2. Isometries on the affine plane will map lines to other lines, and in particular, they'll map points on the boundary to points on the boundary. The difference, though, between hyperbolic space and Euclidean space is that in hyperbolic space, parallel geodesics diverge at infinity, whereas in Euclidean space, parallel geodesics converge at infinity. And so in hyperbolic space, you can't go backwards. You can't take a conformal map on the boundary and induce a well-defined unique isometry on the interior, which would give that. But in hyperbolic space, given a conformal map on the boundary, you can always define a unique isometry on the interior, which induces that map on the boundary via this process. And this is a general thing about cat zeros, so negatively curved metric spaces, or non-positively curved metric spaces. If you take a non-positively curved metric space, you can look at its visual boundary and you get a natural action on the visual boundary, but you can't always go backwards unless your space is strictly negatively curved. And this gives us a natural isomorphism between the isometry group of H3 and the group of conformal maps of the boundary, which is the normal Euclidean ball. How am I doing for time? Good. The more general.
You've still got about half an hour or more.
Cool. So just to sum up, we have natural. I should have mentioned on the previous slide, again, this was an isomorphism of topological groups. So all of this is very natural. The only non-natural thing we have to do is choose complex coordinates. But as soon as you choose a point at infinity, you're doing that anyway. So it's not really a problem. And we want to write down explicit matrices. So of course we have to choose coordinates at some point. What we've got natural isomorphisms between groups of 2x2 matrices in all of these things. So products of circle reflections on the boundary, fractional linear transformations on the boundary, so that was these things. So circle reflections. Biholomorphic automorphisms, so this is something from complex analysis. And isometries of the interior. And so if we take discrete subgroups of any of these should be Kleinian groups. So here's a more full definition. These are all equivalent by the preceding discussion. A Kleinian group we can view, if we have one, as being a discrete subgroup of isometry groups of H3, of conformal maps of the sphere, of groups of matrices in PSL2C, fractional linear transformations, or if you want to view them geometrically as developing groups of hyperbolic three manifolds. And these different points of view are useful in different situations. So these 2 points of view here, well, these ones here are useful for intuition and proving things. So these give you tangible things which you can think about geometrically, and this is giving you something which you can do algebra on. So that's the point of this discussion. We started off with these. So if you remember back here, I gave you this example, and it's not very concrete at all. I mean, I can tell you there is a group which induces this gluing, but this is not giving you much information about the group. As soon as we have an isomorphism with groups of matrices, we have a whole lot of algebraic invariance that we can start using to understand what these groups are. So getting back to what I was saying right at the start about tilings, if you take a Kleinian group, then it will tile hyperbolic three space, but the action on the boundary will not tile the complex the Riemann sphere. It might not even tile an open subset of the Riemann sphere, but if your Kleinian group is nice, then there will be a subset of the Riemann sphere which is tiled by your group. It might tile half of the Riemann sphere with one tile and half the Riemann sphere with the other tile, and leave the bit in the middle untiled. That's allowed, but so this tiling is not necessarily well behaved, but it's just a generalization of this discussion at the beginning that we have a group acting on a surface, and this group is moving a subset around the surface without overlap. It's just that we're losing this axiom that we have to cover the whole space. The maximum subset with G tiles is called the domain of discontinuity, or omega of G. And the tiles will accumulate on the edge of this domain of discontinuity. And the accumulation of tiles on the edge is what causes them to fail to tile the whole space. You'll get a bunch of tiles which tend to be infinitely small until they vanish on some wild subset, which is the limit set, or the complement of this set. I'll give you a picture in a minute, but I want to give you a concrete example. So I take this group with 3 generators. This is actually redundant, so this conjugates S to S tilde and back, but the tiling has 6 sides, so if I want to give an edge pairing, I should give 3 generators. So here's the tiling of the complex sphere. I have this set here with 6 edges, and I claim, and you can check this using you can check this easily by checking where the circles go, that T mu sends this line to this line. I don't actually remember which way T mu sends it. I think it sends this line to this line. It might be T mu inverse. I mean, but T mu and T mu inverse permute these. S translates this vertical line to this vertical line, and S tilde translates, or okay, it's not really a Euclidean translation, but in hyperbolic in hyperbolic space, this is acting as a translation. It moves this arc to this arc, so that's S tilde. In fact, S tilde is moving this entire circle to this circle, like this. And so we glue this line to this line. And let me unwrap this so I lose the geometry, but we get a better picture. So we have a hexagon. I'm gluing that to that. So now I have a cylinder. And the cylinder has two edges on each of these things. And then I glue this to, this to this, and this to this. So I'm gluing this to this and this to this. And after you do all that, you get a torus. So this is in some sense a redundant gluing of the torus, because as we saw earlier, you can do it with just 4 edges. There is, however, something more interesting going on. First of all, this entire real line is not tiled. So if I give you this picture, so the same picture on the left, and then this is the set of, I've taken these 6 circles and I've mapped them across the whole Riemann sphere using the group action. You can see that the tiles accumulate on the equator, which is the real line. And so this real line does not appear when you take the quotient, because we're just gluing the edges of this tile together. So we actually get a puncture. So here's our torus. We get a puncture on the torus, a missing point, which is not appearing in the quotient. We also get, because this group is acting geometrically, we get an induced geometry on this torus. And you can kind of see from this picture that this is heading out towards a cusp. And in fact, the reason this line is missing is because in the Riemann metric on the torus, this point is actually infinitely far away. So this is a cusp. The other interesting thing you can see is that down the bottom here, we have another polyhedron. It's not a polyhedron in Euclidean space, but if you look at, this is the boundary of hyperbolic space. This is actually the boundary of a hyperbolic polyhedron, so it is a polyhedron. Here we have a gluing from here to here and a gluing from here to here. So what does it look like? It looks like this. Remember, this is the point at infinity. So this is not the same kind of point at infinity as this one. This is the point at infinity on the Riemann sphere, but it's just as good as all the other points. We've just chosen a bad chart. We're gluing this to this and this to this. So we get a sphere, but now we have 3 cusps on our sphere. We have one, so these 2 points get mapped onto each other by the group action, so they're the same cusp. Here's a second cusp, and there's a third cusp at infinity, because these lines are parallel. So in reality, they're tangent at infinity. So we actually get a 3 times punctured sphere, a sphere with 3 cusps. And you can see that these are kind of paired here. So you can view one of the cusps on the sphere as being joined onto this cusp on the torus. And so what we've done is we've taken 2 surfaces, the 3 times punctured sphere and the punctured torus. We've uniformized them at the same time with the same group, and they kind of live on the boundary of a hyperbolic 3-manifold in such a way that there is a geodesic in the hyperbolic 3-manifold, which goes around this this bit joining them at infinity. So this is not going around anything in hyperbolic 3 space, but it is a homotopically trivial loop in the 3 space because of this pairing. This is a bit confusing if you've never seen it before, and it's not so important for what we're going to do later on. Yeah. The only thing which is important is the fact that you get this kind of picture. You have 2 Riemann surfaces. And these Riemann surfaces, one of them is a 3 times punctured sphere, and one of them is punctured torus. And of course, this is only happening if I've chosen mu such that this line is sufficiently far up here. If this line gets down here, then my argument about gluing edges no longer works, because this is no longer a connected set. And so it gets more complicated. So you can ask, for what values of mu does this work? Because it turns out that you can actually push mu down a little bit further than here, and you still get the right quotient. And so the quotient is correct. It's just I've chosen a bad way of drawing a polyhedron to make it work. You can draw all the values of mu for which you do get a punctured torus and a 3 times punctured sphere. And that group is the so-called masket embedding of this Beer slice. And it looks like this. So this is the masket embedding of all the mu, such that G mu glues the upper half plane to a punctured torus and the lower half plane to a 3 times punctured sphere. And it's unclear from this picture, but the set of mu is actually the stuff that lies above here and below here. So everything that's close to this is the real line, and this is the imaginary axis. The stuff which lies close to the real line it gives you a degenerate quotient, but everything out here gives you the same kind of quotient as we drew in the previous slide. And this is a quasi-Fuchsian deformation space. It doesn't matter what that means. It's kind of like a moduli space of these surfaces. It actually lies above the classical Riemann moduli space, if you know what that is. It lies between the type Miller space and the moduli space. And the interesting thing about this is the boundary is kind of fractal. And the reason, or not really a reason, but a kind of justification for this is that this is an analog of a Mandelbrot set. So the group action is setting up a dynamical system on the Riemann sphere. You can look at this family of dynamical systems. You can look at the set of places where the family is degenerate and the set of places where it all behaves nicely. And that gives you a moduli space of dynamical systems. And it's exactly analogous to the way that in the Mandelbrot set, you have a dynamical system, which is set up by a single quadratic function. You look at the places where it's wild, you look at the places where it has bounded orbits, and that separates the complex plane into spaces with a fractal boundary, the Mandelbrot set. These words that I've written about quasi-Fuchsian groups, it doesn't matter. This is a technical term. If you know what, this is so that if you want, you can Google the term later, I suppose. I should mention these spaces are incredibly badly understood. For instance, it's not obvious at all that the boundary of the space is homeomorphic to a pair of circles. That is true, and it's true for several other moduli spaces, but there are a bunch of moduli spaces which you can define in this way, where they look kind of the same, but it's not clear, it's not proven. It's an open problem whether the boundary is a topological circle. And I think that's also true for the Mandelbrot set. But the fact that it is known for a lot of these spaces makes this problem of moduli a lot easier or better understood than the problem of quadratic dynamical systems. Even though these groups, I suppose it's because these groups are more complicated. You have more data to work with when you want to prove things. Here's another example. This is kind of a deformed version of the previous example. So this question is going to be a pair of 3 times punctured spheres. And this here is a rotation by 2 pi over 5 around this point. And this is going to be mapping this circle onto this circle. And the fact that you get a pair of 3 times punctured spheres is not at all obvious from this picture. Oh, sorry. So it's even more complicated than that. So we get, again, a sphere with 3 punctures, but now only one of these punctures is a cusp. So we have a cusp here. We have another 3 times punctured sphere here, and then we have 2 cone points on each 3 times punctured sphere, and these cone points are of angle 2 pi over 5. But it doesn't really matter for the purposes of this discussion. Here's one of the cusps, and then these angle points are coming from these things here. And so the space that's shaded in is the space where the orbits accumulate. So this is the analog of the real line in this picture here, except I haven't drawn all the images of these other circles. I've just drawn what you get when you continue to the limit. So that's the limit set. And the space which is tiled by the group is the space which is not the limit set. And in this case, it's a circle packing. And the fact that it's a circle packing is giving you some indication that the space of these surfaces is somehow rigid, because you can't deform a circle packing and stay a circle packing easily. Whereas here, you can deform the real line and you still have the same, while keeping the same structure of orbits. You can move the real line slightly, it moves the space of orbits slightly, but it's possible to deform them. Here, it's not possible to do that and keep the same structure. And this is a so-called Rayleigh group. This is a Mascot group. This is a Rayleigh group. Here's an old example from 1897, and this is from a book by Fricker and Klein on automorphic functions, which I have got some slides on, but I don't have time to talk about them today. But basically here, what they've done is they've taken all of these circles, which you can see, which form this chain, and they've taken the group which is generated by the reflections in each circle. And then you have to pass to the orientation preserving half, of course, because a single reflection is not orientation preserving. But once you've passed the orientation preserving half, then the limit set is this fractal line. And the reason for that is that if you look at an individual circle, the whole of this chain of the exterior is mapped onto a chain on the interior, which goes from one side to the other, and in the limit you get a line, and that's this line here. And that is a topological circle. In fact, this sequence of circles is giving you an addressing of points on this topological circle, like decimal expansions on the real line. It's exactly analogous. And using a similar argument to give the topology on the real line via Dedekind cuts or whatever, you can induce a topology on this line, on this curve by cutting circle chains, and that gives you a homeomorphism between this and the standard real line with point infinity, or the circle. I haven't written down matrices for this group, first of all, because there are a lot of generators, and second of all, because it's just hard. Even in the case where you've just got a few generators, it's complicated to write down matrices. There are far too many parameters. Nevertheless, they do so in this book. So it just shows that in the 1800s, people were far less scared of matrix calculations than we are now. It's a hideous matrix representation, but you can, in principle, write it down. I think in the interest of time, I'll skip this example and just go on to some arithmetic examples in the last 5 minutes. So PSL2Z is certainly a discrete subgroup of PSL2C. Oh, I forgot to mention, I was giving everything the compact open topology, whatever that means. But it turns out once you pass to matrices, this is the same as the topology which you get when you view a 2x2 matrices as a vector of 4 elements and take the normal Euclidean topology on that. So discrete groups of matrices are just discrete when you view these as points in R4, in C4. So with that, it's obvious that this is discrete. It's just Z4 modulo some quotients. I think it's less well known. You don't really learn this in an undergraduate course, that PSL2Z admits a presentation by 2 matrices. This one here is a translation by 1, and this one here is an involution which takes this unit circle and it maps it across like this. So you get a tiling of the upper half plane by triangles which look like this, and in the quotient you get a cusp which comes from the cusp of infinity, and again 2 angle points, and these angles are going to be 2 pi on 3, because this is I think it's 2 pi on 3, you get these angles. A group of finite index in PSL2Z is also discrete, and it's called a modular group. And so just in the last couple of minutes, I want to tell you what this has to do with Fermat's last theorem. So This is a technical notion. So I define modular groups as being groups of finite index in PSL2Z. Many of these are of the form you take all of the matrices in PSL2Z and you reduce them at mod n for some integer n, and these groups are congruent subgroups of PSL2Z, or groups which lie in between these subgroups and PSL2Z. So you have these subgroups, gamma n. You have up here the full modular group, and in here lie the congruence groups. So these are the groups which reduce mod n to the identity. Yeah, these reduce mod n to the identity. These ones contain all the matrices which reduce mod n to the identity, and maybe some extra data on top of that. Why is this important? So the result which Andrew Wiles actually proved in the 1990s when he proved Fermat's last theorem was a special case of the following result. If you take an elliptic rational elliptic curve, then it comes from a modular form. He proved this a special case of this, and I'm going to state an even more special case. So I take an elliptic curve E. I can always write it in this form. So it's a curve given by the zero set of an equation which looks like this. And I can define a function on E, which is this function. This is actually, if you know any of these words, this is an automorphic form on PSL2Z, weight 0. But it doesn't matter. It's just a function in terms of the coefficients of this polynomial. It's got this weird number 1728. That number is just to make this work. I mean, this is basically a statement about invariance under the group action. And the theorem, which is a special case of this modularity theorem, is that if this number is rational, then the elliptic curve is actually the holomorphic image of a Riemann surface which you get when you take the quotient of hyperbolic 2 space by one of these congruent subgroups. So these elliptic curves can be quite wild algebraically, but you can always get them holomorphically as the image of one of these very nice quotients. And these groups here, these are very nice rigid groups. So in some sense, this is telling you that whenever you have an elliptic curve, it is carrying a lot of this arithmetic modular data. I think it's basically all I have time for. Let me just go through the rest of my slides and see if there's anything I want to mention. Oh yeah, so I won't go through any of these details, but you can generalize this construction of PSL2Z and finite index subgroups in PSL2Z to non-commutative algebras and global fields other than the rational numbers. And you do this by looking at quaternion algebras. If you look at the group of units of a quaternion algebra, then roughly speaking, that is a Kleinian group. This is an arithmetic Kleinian group, so it's not just carrying geometric data, it's carrying arithmetic data in exactly the same way that these elliptic curves are carrying arithmetic data as group quotients. And there are lots of examples that you'll learn about if you do analytic or algebraic number theory. Basically, the interest from the geometric point of view is these are well behaved with respect to volumes. So the figure 8 knot comes from an arithmetic group, and it's the only knot which comes from an arithmetic group, but infinitely many links, so knots with more than one component do come from arithmetic groups. And you can see that it's arithmetic here because this is lying in a finite index extension of the integers. That's basically the idea. And finally, yes, so the last thing I want to mention is if you look at the space of all closed complete hyperbolic three manifolds, there is one of minimum volume. And just to give you a final example of a Kleinian group, I want to show you what the Kleinian group of the hyperbolic manifold, the closed hyperbolic manifold of minimum volume is. It's called the Matveev-Fomenko-Weeks manifold. It has volume 0.942707 ... And in 2009, it was proved that this manifold was the smallest possible volume closed orientable hyperbolic three manifold. it comes from this polyhedron, and it is tiled by the group generated on 9 generators, which I've lifted here. I mean, it's impossible to understand what this is saying, but the point is you can write down these generators, and this is something I only found out yesterday when I was looking for pictures of this manifold. So I knew this manifold existed sort of from the mathematics point of view, but I found these pictures in an astrophysics journal. So somehow this is, I don't know how actually interesting in astrophysics it is, but there are people who call themselves astrophysicists publishing in astrophysics journals who care about these manifolds. So in some sense, I suppose these have a practical, I mean, they have an application in the sense that physics is applied, but this is by no means applied physics. So if you want applications, probably this is not helpful for you, but it's something. Great, and I'll leave you with a list of books which are much easier to understand than this talk. So thank you for listening.
Thank you for your talk, Alex. Does anyone have any questions? Well, I might ask a question or two. One thing I was wondering is there kind of like a classification of Kleinian groups or certain classes of Kleinian groups?
So there are a bunch of different ways of approaching that question. So if I start with the surface case, so the Kleinian groups, which gives you just a surface, are actually called Fuchsian groups. They're PSL2R or conjugates of subgroups of PSL2R. And those are in some sense classified as soon as you've classified Riemann surfaces. And this is what you do in moduli theory and type Euler theory. So you look at type Euler space and moduli space. Type Euler space is giving you all of the metrics on your surface. Moduli space is what you get by when you quotient out by the different ways you can put the different ways you can commute the structure around on your surface, so that they're measuring kind of the same thing. And even the study in the surface case of these moduli is hard. For instance, I think there is no explicit construction of moduli space in terms of equations or anything for any genus that's higher than, say, 1, or number of punches higher than 3 or 4. This is a hard problem even for surfaces. For Kleinian groups, so this is something I didn't mention, but there's something called the Beer's Uniformisation Theorem, which says that if you have a countable collection of hyperbolic Riemann surfaces, there is a Kleinian group which uniformizes them. So solving a classification problem for Kleinian groups is equivalent to solving countably many problems for surfaces, and that's already an intractable problem. There are classifications, though, for subtypes of Kleinian groups. And one of the ways of doing that is with this theory that I've mentioned here. So what you can do is you can look at the different representations of a fixed Kleinian group, and you can look at the quasi-conformal conjugates of fixed representations, and that gives you a kind of moduli space as well, and that's a picture which I've drawn here. But this is just classifying the Kleinian groups which are giving you a fixed quotient. It's by no means classifying, this is in fact a low-dimensional slice through the space of all of the punctured torus groups. So this is even smaller than just the moduli space of all Kleinian groups, which gives you punctured tori. And even this is intractable. I mean, it's possible to do this theory, to work out a nice theory in the case of the punctured torus, and also in the case of the 4-time punctured sphere, and in various other groups. But all of the cases that I know of where this is possible are when you take slices through the boundary of the moduli space of Terrae of genus G. So they're not classifying anything wild. They're just spaces on the boundary of the most simple surfaces you can write down. So to answer your question, is there a classification? Yes, in some cases, but in general, no, and probably there's no hope of there ever being. These groups are just far too wild and diverse.
And this might be a silly question, but I don't really understand things too well. Do you ever get Kleinian groups that are not finitely generated?
Yes. In fact, this example which I skipped over, this group is, okay, I have an annulus, which is the bit in between these two black circles. I've got a blue spiral, which is wrapping infinitely many times around, and a black spiral, which is wrapping infinitely many times around. On each spiral, I have a chain of tangent circles, which is leaving gaps in between. So these chains separate the plane into 4 regions: this orange unbounded region, the red and the green regions which lie in between the chains, and then this interior which is pink. And I take the group generated by all the reflections in these circles. Obviously, it's infinitely generated as I've written it, but that doesn't mean there's no set of finite generators. However, if you actually do a bit of analysis, you can show that the green and the red regions give you they give you Riemann surfaces as quotients. But why is that? Because these reflections always map the green onto something adjacent to the green, and the red onto something adjacent to the red. So the quotient is nice and well, it's mapping nicely. But these orange and pink regions are always mapped into the inside of one of these circles, and then into the inside of one of the other circles, and they're never mapped onto something which lies next to where they started. And so these always map off themselves. They're called atoms. They have no non-trivial stabilizer in the group. And the existence of these atoms tells you that there exists no finite generating set for this group. This is because there is a theorem called the Elforce Finiteness Theorem, which says that whenever you have a finitely generated group, all of the quotients are Riemann surfaces of finite type. That is, they look like this. So if you ever get anything to generate, it means that you kind of started with a group which is finitely generated. So this is probably not the easiest example of an infinitely generated Kleinian group, but this is the example that I have.
Okay, thank you. That answers my question well. Did anyone else have any questions for Alex? Well, if not, let's thank Alex again and we can finish things here.
Thanks.
Thanks for your talk.